Welcome to the project demonstration of solar maximum power point tracking with SEPIC converter for agriculture water pumping system. So here we are using the SEPIC converter. So as you know that SEPIC converter is nothing but single-ended primary inductor converter. So this is the SEPIC converter we have developed with help of two inductors and two capacitors and one diode along with one MOSFET. So here we are using the MOSFET of IRF-Z44 and diode is a 10 amp diode, so which is in forward bias from input section to output section, and these two inductors and two capacitors are used to charge and discharge whenever we are triggering this MOSFET. So this capacitor is connected across the load. So in our project our battery is the load and this capacitor is used to discharge and charge based on the MOSFET triggering one. So here the main application of this project is maximum power point tracking. Means as we know that when we place the solar panel, 12 volt solar panel under the sunlight. So here we are using the 12 volt 10 watt solar panel. So when we place this under the sunlight, it will provide us the maximum of 18 volts. So as we discussed, the current rating is 10 watts. Means the wattage is going to be 10 watts. In order to maintain the wattage equal to 10 watts, then our solar panel will reduce the current whenever the voltage is increases. Means 1 amp current and then nearby 12 volts, we will get around of 12 watts of power. Assume that. And whenever the voltage increases, in order to maintain the 10 watts or 12 watts of constant power, then parallelly we are going to, the current will be decreased. So then the output power is going to be the constant irrespective of the voltage levels and current levels. So at that point we are going to get the low current when we are getting the high voltage. Then our system will control the voltage with help of this SEPIC converter in order to gain the maximum power. Means whenever the voltage is crosses the 14.5 volts, when it reaches to 18 volts. So when it start the point of 14.5 crosses, then our microcontroller will start control the trigger pulse, means duty cycle to this MOSFET to reduce the voltage of the output of this our SEPIC converter. So then the voltage will be regulated and locked at the 14.5 volts, and then the current parallelly will be increased. So at the some point of time, maximum voltage and maximum current reaches. So that point is called as a maximum power point, and that will be tracked with the help of our PIC16F72 microcontroller. So coming to the application, so right, successfully the solar panel generated the voltage and our microcontroller measured that and controlled the voltage, and the maximum power point reaches and the battery got charged with the maximum power, so that the charging time also will be decreased. So generally without using the SEPIC converter, it may take 8 hours to 10 hours constant voltage when we generated from the solar panel. Then it will 8 hours to 10 hours the battery will be fully charged. With the help of solar this SEPIC converter, the charging time will be decreases to 5 hours only. So that is the main advantage of our SEPIC converter here. The application in our project is agriculture application. For that purpose we are making use of this DC water pump, PMDC water pump, for pumping into the agriculture applications. So coming to the SEPIC converter operation. So whenever the voltage is this we need to connect at this slots. S for the solar panel, and this is the transformer section. As we are providing the secondary source to charge our battery whenever the sunlight is not available during the night times, then we can charge a battery with the help of this transformer. Just connect the 230 volts AC input to this plug, then the charging light will show the status. Same like if you place the solar panel under the sunlight, this light will get switched on, so which is present on this charging circuit of this solar panel to the battery. So if you want to charge a battery from the transformer, same, it will take around of 8 hours to be fully charged. Next, solar panel is connected over here. So from this charging circuit we are providing the input to this voltage sensor. So there are the two voltage sensor. Why? Because we need to measure the battery voltage which is connected at this SEPIC converter output, as well as SEPIC converter input voltage, nothing but solar panel voltage. So these two continuously monitored from this voltage sensors. So here we are using the 10:1 potential divider circuits. As we are getting 12 volts maximum, means 18 volts of maximum, our microcontroller can't measure the voltage which is greater than the 5 volts. So we should make the input voltage below 5 volts only. For that purpose, we are dividing that 10:1. Means whenever the controller gets 1.2 volts from this potential divider circuit output, that is considered as the input of 12 volts, means 1.2 into 10. This calculation will be done inside the microcontroller in embedded C language. So parallelly we are going to display the respective voltages on the LCD screen, which is the input and output of this SEPIC converter here. So coming to this charging circuits, so both charging circuits look like same. So both has the rectifier section and filtration section and unidirectional diodes. So rectifier is useful for this transformer inputs, which is act as a AC to DC converter. But coming to the solar section, this rectifier will act as a polarity corrector. Means if we connect this solar panel in reverse polarity, it plus to plus, minus to minus, normal. Plus to minus, minus to plus is reverse polarity. In that case, if we place this 4 diodes, they will rectify the input to plus, minus to minus instead of minus to plus, plus to minus. So that we can protect the battery from reverse polarity connections. And output of this charging circuit is input to the SEPIC converter. Then the control will start reading the input from the solar panel and then it will check with that. So coming to the SEPIC converter operation, so initially consider this capacitor under fully charged, okay, and next when we on this MOSFET, so already the inductor and capacitors 2 are in charge condition only. So let me show you the circuit diagram of our SEPIC converter, right? So this is the SEPIC converter circuit diagram. Right, let me explain you the parallelly. So this is the input, so this is the input, and the next, so we have connected the inductor, so this one is the inductor, and the switch, so this S1 is the MOSFET switch, and this is the capacitor which was connected over here, and the next L2, L1 and L2, this black color one are the inductors, so L1 and L2. So we didn't connect this capacitor as we are using directly solar panel with high wattage. Next, this diode D1, so this is the D1 diode, 10 amp diode, which we discussed, and the capacitor is C2, so this is C2 is the capacitor. So C1 and C2, L1 and L2, this is the S1. So whenever we switch on this, initially we have to open this one. After this, consider these two are charged, and when we off this S1, so when we off this S1, here the L1 inductor and C1 capacitor will charged, and when we on this start discharged, then automatically L2 will charges. Then after when we on this again, so it start discharging. The output from the C1 and L2 is input to the capacitor C2 through this diode. So based on the on signal duty cycle to this S1, the charging and discharging time of L1 and L2 will varies. Means if we on this one, this will charge. When we off this one, this will discharge, and the capacitor will charges again. So based on this switching sequence, our time of charging and discharging will be increases. So when we increase the charging discharging time, we will get the more voltage with respect to the input voltage, and when we decrease that, then output voltage will be decreases. So SEPIC converter main purpose is we can increase the output voltage with respect to input, we can decrease the output voltage with respect to the input voltage, and also we can make it constant. So the main advantage of this SEPIC converter is directly we are going to get the same polarity output with respect of the input, means plus minus, output also plus minus. So whenever the voltage increases on the solar panel, automatically our controller will control the voltage when it is above 14.5 volts. And coming to the application, just on this, there we can see the, so we can see the voltages. As of now, low lighting, so low voltage we are getting, and the battery voltage is 11.86. Coming to the water pumping in and out, so place this in. So now this is the output, just on that switch. Right, so the water is pumping.